don't see it recording. So hopefully you see a little message that it's recording now. And then that way everybody can catch up if they are having connection issues. To work on to get ahead for the next ALEKS assignment. And I will start today with talking about the content itself. So lecture slides right here. The matter, chapters 1, 3, and just that one section of chapter 5. So you can click on that to open it if you want to follow along on your own computer, or you can just watch on the screen here. So we're here to talk about chemistry, excuse me. It's really helpful if you read ahead, if you look at the keywords, or watch videos so that you know the words already that we're going to be talking about when we start. And that way when you hear what we're talking about, when you hear the content, it's not the first time through, it's familiar. And what that does of generating those questions, you have more memory of what you learn, because you had an idea, you ask a question, and then you get something clarified. So it's really helpful to work ahead before the lecture, even though sometimes it feels like it's not very productive. So do try to work ahead as much as possible. And try to get ahead on ALEKS. I've set those up so that the due dates give you plenty of time to earn the grade, but really that content may come on the exam or quiz before the assignment is due. All right, so best approach to learning chemistry, read ahead. Take a look at the vocabulary words. It's useful to see them and say them. And that way when you hear it again, you already have that familiarity. And one of the trickiest parts is when we have common vocabulary words that we already know and use, but they're used in a very technical way. So they mean a very specific thing in chemistry, and that can be confusing because we have to redefine words that we already know. So that's one of the trickier parts, I think. Let's see, there's a couple things that you have to memorize. Oh, I'm not having you memorize polyatomic ions. Those will be given to you on that printable periodic table, so you can see exactly what you have. So you will be given those polyatomic ions, and you don't have to memorize them. You do have to know how to use them, and we'll talk about it much more. One thing that we do still memorize are the metric prefixes. So that's things like kila and centa and milli, and we will get to those too in chapter 2. So those will be some of the content that you need to know, and know means memorize. We will learn a couple systematic ways of approaching problems. One is problem solving in general. Dimensional analysis is using the units to solve the problem. And there is normally some resistance to that process, especially if you've learned math kind of a different way first. But it's very powerful and it generalizes really well. So it's something that once you use it will be useful in all areas of life. It's really very helpful in the grocery store, or many people are in pre-nursing. So as a nurse, you would need to be able to calculate dosages of medicine, for example. All right, and then systematic naming. There's a lot of common names in chemistry, but I'm not asking you to know those. That's just memorization. But except water, have to know that one. But there are systematic names, and we will use those because you can develop a process that gets you the right answer every time. All right, as you're working through the textbook, as you're reading, it's useful to do those problems. You can cover up the answers for the examples and work through them line by line, and that's really helpful. I like the way that this textbook approaches chapter 2, doing those calculations. So that's one place to get some good practice. Okay, so what is chemistry? Chemistry is the study of matter and the properties of matter and how matter changes in contact with other matter or over time. So we have to have a definition of matter. What is matter? And that's not as straightforward as we might think. Historically, people thought there might be ether, that was some unseen force that causes life. Matter, for our definition, is anything that takes up space. It has volume, it has mass, and air included has mass and takes up volume. It's small, but it's there. So anything that you can see or touch or smell, there has to be something there, some matter. And then the properties of matter are the characteristics. We have physical properties like what color is it? What does it taste like? We have chemical properties that describe how it interacts with oxygen or other substances, how it interacts with other substances. And then transformations are how those properties change over time. So we'll look at some of those more closely. Here are some examples. Physical properties are those that can be changed without changing the original substance. So you can, sorry, I was thinking of physical changes. Physical properties, yeah, can be changed without changing the composition. So for example, we talk about melting and boiling. You can take an ice cube and melt it, and that would be a physical change because you could freeze it again and get that same ice cube back. So that's what I mean, it doesn't change the composition. Things like the color or the odor are physical. Chemical properties are things like the reactivity. Does it tend to explode on contact with air? Does it tarnish or oxidize? And so we'll talk a lot more about that in the oxidation chapters. We can also talk about intensive versus extensive properties. An intensive property is something that does not depend on how much is there. So the temperature is a good example because you could have a cup of water at a certain temperature, or you could have a giant swimming pool at that same temperature. The temperature doesn't tell us how much matter is there. Extensive properties depend on the extent of the sample. So if you have a small piece of cake or a large piece of cake, the mass will tell us which one it is. So it does depend on the extent of the sample that you're working with. So mass and volume are both extensive properties. I also like to begin with a look at starting with the macroscopic world, what we're familiar with. So macroscopic means about the size of your hand. So from like the thickness of your fingernail up to something that you could hold. Something that you experience in real life would be in the macro scale, macroscopic. So in this picture, we see the fire, right? You see the logs and they're getting burned away. They're going to leave ashes. And you see the big flames, big yellow flames. And that change is observed because of the change on the molecular world, on the molecular level. So the structure of the logs is interacting with oxygen. It's been initiated with a spark, right? We started the combustion, and the log is getting transformed, completely obliterated, and turned into carbon dioxide and water. So we can see in the, I think, can you see my mouse? You can see the CO2 molecules and the water molecules, and this is a carbon oxygen, carbon monoxide. So there's a mix of gases that's being generated. So that log turning into ashes shows us the macroscopic representation, the real life representation of the conversion of big cellulose molecules into these smaller particles of gas. So that's really what we're going to be doing. We're going to be thinking about what we experience in life and understanding on the microscopic level what causes that. All right, so fundamentally, the structure of the microscale determines the properties on the macroscale. So everything's made of atoms are the smallest pieces of one kind of element, and molecules are multiple elements together in the smallest particle of a substance. So here we're looking at carbon dioxide. There's a carbon in the middle, right? So there's one carbon and two oxygens, and they are laid out in a linear format here, and we're going to learn about that and see that that is responsible for it being a gas at room temperature. Water has an oxygen and two hydrogens, so the elements are different and they have a bent shape. And we know that water is a liquid at room temperature. So we're going to learn about how to predict those shapes, how to draw the structures, and predict the state of matter at room temperature, for example, based on that information. That's something we'll spend a lot of time on. All right, scientific method. Scientific method is an iterative process, and it's used to remove our biases and what we expect from the process of observation. So we make observations and we come up with a potential explanation of why something might be happening that is testable. It has to be testable. And then we set up a series of tests. We try to make our assumption fail. And if it never fails, we test it over and over and over again, eventually it becomes accepted as a theory. Then once that theory has been tested again over a long period of time, everywhere in the world, then we might draw a statement from it that is a law. So a hypothesis is this idea, this possible explanation of why something happens. And it has to be testable, because if you say, well, it happens because of this, then you need to set up conditions that test that reason why. If it fails once, it's disproven and you have to restructure your hypothesis. But if it never fails with all these different observations that are made, then it becomes accepted by the scientific community, and a theory can be drawn as to a predictive model as to why that occurrence happens. So I like this little diagram here where you can think about observations. Observation is one thing happens, right? So let's say we knock a pen off the table and it falls to the ground every single time, right? So that one observation might lead us to a hypothesis, right? There are lots of hypotheses we might have. We know that pen falling is governed by the law of gravity, which says that two objects accelerate towards each other on the basis of how much mass they have. So knowing that, it makes sense that the small pen always falls towards the huge earth, right? But of course that process happened by hypothesizing what it could be, making repeated observations, so going back and forth until it's determined that that hypothesis must apply to all events. And then once you've developed your theory, then you can draw from it the law, which is just the statement of what happens. So observations and laws describe what happens. Hypotheses and theories explain why they happen. All right. So just a little bit of historical construction. Lavoisier gave us the conservation of mass, and that was determined by careful experimentation. Up to that point, there were not very careful experiments. It was hard to make measurements. So that was really revolutionary in that sense. He created a closed container where he weighed the container in advance, and then he started a combustion reaction and he weighed it after. And he found that those masses were the same before and after. So if you think about that from a more historic perspective, we might expect, like, you weigh those logs and then afterwards you weigh the ashes and the masses are different, right? Where did all that material go? Well, he contained it all in one container and weighed it before and after and found out they were the same. So it turns out that that mass from the log was transported into the vapor, into the air. And so that was a really revolutionary finding at the time. And Proust gave us the law of constant composition. It says basically every carbon dioxide molecule has one C and two O. It doesn't matter where it is in the world, but it's always the same if it has those same atoms laid out in the same way. So those are some of the fundamental discoveries that underlie everything we talk about. And then Dalton came along and said, well, there must be some smallest fundamental unit of matter, and we'll call that the atom. He made a lot of proposals. He thought, and he was wrong on one of them, he thought that every atom of an element was the same. They actually have slightly different masses, and we'll learn about that when we get to isotopes and atoms. But he was putting things together from many different sources of information. And we're going to start by classifying matter in a more, according to Boyle's approach. So we're going to divide matter into pure substances or mixtures. And first we'll look at pure substances. Pure substances can be either elements or compounds. And elements are found on the periodic table. Right, so if it's on the table, it's an element. If it's not on the table, it's not an element. So that simplifies that matter. Now, compounds are at least two different elements connected together. So two different elements, but they're still pure substances. So our examples here are copper. Copper is just that one copper atom all together in that lattice array. This is sugar. So we can see those shiny crystal surfaces, and each molecule has carbon, oxygen, and hydrogen. They're all acting together as a unit. So it's still a pure substance, even though it's got multiple elements on it. All right, then we'll look at mixtures, and we'll break them down as to whether they are homogeneous or heterogeneous. All right, so elements. Elements are found on the periodic table, and they cannot be decomposed to any simpler forms. If you break down an element, then you venture into high energy physics. Those things are like if you break a carbon atom down, you might get subatomic particles, but it no longer has the properties of a carbon atom, right? So elements are the simplest form that can exist with chemical transformations. Compounds have two or more elements. Compounds are defined by having that fixed proportion. So that carbon has, the CO2, carbon dioxide has one carbon and two oxygens. And water has two hydrogens and one oxygen. And that fixed proportion is what we're going to look for to know if something is a pure substance or not. So let's look a little more at elements. Elements have unique properties, but they have different abundances. They have different distributions throughout the world. So if we look at the whole universe, 91% of the universe is hydrogen, and 9% is helium. So all of life exists in this very small percentage of the universe. If we look at the Earth, at the surface of the Earth, 60% is oxygen. So why would that be? Where's all that oxygen coming from? We might think of the air. The air is only 20% oxygen. It's actually mostly nitrogen. So 60% oxygen. Soil, there's a lot of carbon in the soil. There's some metals. And most of the oxygen is because of the water on the surface of the Earth. So if you think of the oceans and all of those water molecules, water is mostly oxygen by mass. So that accounts for that huge amount of oxygen. In living systems, we have mostly carbon, hydrogen, oxygen, and nitrogen. And these are right on the top of the periodic table. All right, maybe I have to turn off my background to make this more visible. Oh, nope, still not working. Here we go. All right, so carbon, nitrogen, oxygen are over here, and hydrogen's over here. So we're gonna learn a little more about why hydrogen's on that side. it's probably useful to print out the periodic table, the printable periodic table. It's got the polyatomic ions down here, so that you have it during class time, and then you can refer to it and see it on your paper, not relying on a little picture. So that's probably a useful strategy. Okay, get this, there we go. All right, on the periodic table, each element has a symbol. We have completed the periodic table relatively recently. These guys over here, these elements. So when I was in high school, we stopped right about here, radium. A bunch of these were not yet discovered, but now we've gotten to the end. And so we think the periodic table is complete. Now, if we discover another metal down here, okay, then we're in big trouble again. All right, let me check the chat window. Oh, yes, where are the lecture slides? I'm gonna take a little pause and show you where the lecture slides are. All right, so under course resources, you'll open that up. Now this top part is just the syllabus, and I have that just for another day or so, and then I'll move it to the bottom so you can read if you need things. Here is the periodic table. This, you should probably print that periodic table, and also the fill-in. The fill-in periodic table is gonna be useful too. You could start that anytime. Again, that's just for you, for your work, for your reference and memory. It's not an assignment I'm gonna collect. Okay, worksheets, those are the ones I'd like you to print or have on a notes type of device. But then the lecture slides, oh, and then I added the class recording from yesterday. Here we are, matter, chapters 1, 3, and 5, essentially. So this is where the lecture slides are that I'm working from right now. So that said, you don't really need to take notes. If you are going to print the worksheets, which is a good idea, then you could potentially take notes right onto there. All right. Some of those symbols correspond to the names that we're used to, like carbon and oxygen and hydrogen. So those have just one letter, like C-O-N-H. But some elements have two letters. Now, if they have two letters, make sure the top one, the first one is uppercase and the second one is lowercase. So if you do them in all caps, it doesn't look like an element. So make sure that you conform to that style of expressing the elements, just like you see on the periodic table. All right. Now, some of them come from Latin or Russian names. So here are a few of the funny ones. Na is sodium. In Europe, it's called natrium. So that is right here, right up at the top, sodium. Potassium gets a K. It's right below sodium. P is over here, right? What's P? P already got taken before potassium. So what is that? Anybody know?
Phosphorus.
Oh, what's that?
Phosphorus.
Yeah, that's right. That's right. Awesome. Okay. Yeah, so phosphorus, that was used on those green CRT screens. So if you've seen really old computers with that green color, that's phosphorus. Iron. All right, iron is Fe. Oh, I'm gonna try to annotate here. Okay, so let's see. I usually try to make some jokes to help remember. I'm not funny at all. So I know that, but let me just see. Sometimes it helps memory. So what is this? This is iron gets the symbol Fe. So what is this? Oh, it has to be capital and then lowercase. All right, and then I'll give. Anybody know what I'm trying to draw here? All right. Oh, you know what I'll do? This should be a little further. All right. Well, it's supposed to be a Ferris wheel, right? So Fe stands for ferrous or ferric for iron. So just one way to try and help remember iron is so important that we have to know that Fe. And then copper is Cu. We also have Co, number 27. Number 27 is Co. This is cobalt. Cobalt. It's not quite as common as copper. Copper is very common. So Cu, cupric or cuprous. We also have silver and gold, Ag and Au. And those are right here. So you'll notice copper, silver, and gold. Cu is copper, Ag is silver, and Au is gold. And right below that is platinum. So those are the coin metals, right? Those are the things that were traded to hold value. They resist oxidation. And they kind of go from like pennies were copper, and then dimes were silver, and gold bars were more expensive. So they're increasing in value as they go down. And that was how I remembered the difference between the silver and the gold. We also need to know Pb, lead, Pb, plumbus. It's right down here. And the Romans built their pipes out of lead, their plumbing. But of course, lead is toxic, and they all went crazy eventually and lost control of their empire. So lead is still an issue in Flint, Michigan. So still a relevant issue there. All right. Then tungsten is W, and that's way over here. That's you don't really need to know it. It's right over here. But it was one of the first filaments. So in light bulbs, they would stretch a thin wire and run electrical discharge across it, and it would glow. So it's still used in scientific instrumentation, but historically it was very important. All right, I like this picture because you get a sense of what things look like. Aluminum, you know, in those ingots, it's not as flat and shiny as when we have a roll that's all, you know, processed for us. But it is that shiny metal color. Carbon, it's like black, right? It looks a little bit like these iron filings. These iron filings probably would feel different. Okay, thanks. All right. Okay. So comparing the carbon and the iron, carbon's kind of lumpy, like charcoal got pulverized, but these are pretty regular. They're pretty smooth, a pretty smooth pile there. Copper has that characteristic color. Gold, similar, has a different color, but it's very characteristic. And here's silver. It has just a little bit of tarnish on there. But I like these names too. Copper comes from cuprum. Gold comes from aurum, like Rising Dawn, I think was how it was named. Ferrum, plumbum. Mercury is hydrogarum. I don't even know how to say it. Okay, kalium for potassium. Argentum, natrium, and stannum, Sn. Sn is right above lead, and Sn is tin. So we do see tin around in solder. Tin cans are usually made out of aluminum, but we do see tin around. So Sn, stannum. All right. All right, so those are the elements. They are 100 of our closest friends on the periodic table. They're all a little bit unique, but then they all have some trends too. So we'll be looking at those. And they are pure substances. We also get pure substances that our compounds are made up of more than one element, and we use a chemical formula to represent those. So in the chemical formula, we will use subscripts to say how many of each kind of atom. If there's no subscript given, then it's assumed there's one of them, right? Because if it was 0, it wouldn't be written. So water has 2 hydrogen, 1 oxygen. And the next one is methane. CH4 is our smallest hydrocarbon. So it's used as a fuel. It's got 1 carbon and 4 hydrogens. The next one is a sugar. I just recognize it from knowing that. But it's got 12 carbons, 22 hydrogens, and 11 oxygens. Okay, so that would be like a sucrose or glucose. And those are pure substances. They could be broken down. You can break down sugar into carbon, hydrogen, and oxygen. So some familiar compounds are table salt is NaCl, sodium chloride. Sugar, you don't really need to know the formula, but it is a pure substance, and we will see it a few times. Water, we've talked about. Baking soda is, we're going to learn its name as sodium bicarbonate or sodium hydrogen carbonate. But that's a household chemical that we should be familiar with. Acetic acid is the active ingredient in vinegar. So those are some common compounds, and you can tell they're compounds because they have two different elements, and they are they appear in a fixed proportion, right? If I wrote H3O, it would not be a water molecule. Does that make sense? All right. All right, so next we get to mixtures. Mixtures are combinations or two or more pure substances. So one mixture to think about might be salt with sugar. If you mix salt with sugar, they're gonna look similar, aren't they? They're both crystals that are white and shiny. But if you taste them, you can taste it's not pure, right? So if you have a little bit of salt in your sugar, it will taste mostly like sugar. If you have a little bit of sugar in your salt, it will taste mostly like salt. So the properties vary as the proportion varies. I think my favorite example is coffee, black coffee versus having cream in your coffee. And you can tell if you drink coffee, you know if you have the right amount of cream in there because the color tells you. You can see, oh, it's too dark. I want a little more whitener in there, right? Chocolate chip cookies, another example of a mixture. And we know that because we can see the different colors of the chocolate chips. So properties like color, flavor, the melting point, right? You take those cookies out and the dough is solid, but the chocolate chips are still liquid. So that's a difference in melting point, physical property. When we talk about mixtures, we need to classify them as heterogeneous or homogeneous. So are they lumpy or smooth? In this picture, we have the air showing those gas particles. That blue one is the nitrogen and the red one is the oxygen. And then down here, they're showing that ocean water. So the water is a little red and white. And then they've got these balls. These are the sodiums and the chloride ions showing salt water. All right. So when we're trying to decide if a mixture is heterogeneous or homogeneous, we're going to take a sample that we would handle on the macro scale. So if we're talking about something like lake water, you would scoop up a handful and look at it. We wouldn't necessarily want to look under a microscope, right? Just a normal sample. So sometimes people have different answers based on what they're visualizing. And it's always a good idea to write down that thing that you're visualizing. All right, so one way to tell is how many visibly distinct phases, like that chocolate chip cookie. Can you see one part's white and one part's black? Are the properties uniform? Now, if the properties are uniform, it could be a mixture or it could be a pure substance. So you might need a little more information. One of the really important things about mixtures is they can be separated.
Could you go back for just a second?
Yeah.
Thank you.
So if it's a mixture, we can get our original substances back. Now with a coffee with the milk in it, that would be hard to separate. But some things are easy to separate. Both of them are mixtures. So we can usually separate mixtures on the basis of their physical properties, and one of those properties is the boiling temperature. So we could separate salt and water. If you had salt water inside a mixture here, and you boil off the water, and then it's gonna run down this condensing tube. There's cold water on the outside, and the water by itself will drip out the end. So then in here, you would actually not heat it all the way dry. You just let it evaporate at room temperature at the very end. But we'd end up with salt crystals all inside there, leaving the salt there and separating the water off. So we can get those substances back, those pure substances. We might also use the same process to put wine in here. Let's say we have wine, it's a mixture, and we want to get just the alcohol. The alcohol will boil first. So we'll add heat until we get to the boiling point of the alcohol. That alcohol is in the vapor right here and it travels in here. Once it reaches that cold glass, then it goes back to the liquid and drips out over here. So we know when that temperature goes over the boiling point of alcohol, it's time to move that water out of there. Move the container away, because that's the alcohol. And when the mixture starts getting hotter again, the alcohol has all been removed. So this is distillation. It's separating a mixture into its pure substances based on a difference in physical properties, in this case, difference in boiling point. We can also look at this mixture. Here we have potassium dichromate is orange, and we have those iron filings that are the black magnetic particles. So using that magnet, we can gather up the iron and then maybe tap it out on the side and then keep going until they're completely separated. So again, the physical property that we're looking at is a difference in magnetism, and we can get our original substances back by separating that mixture. Here are some physical properties. Many of them are familiar. So things like the color or the shape or the odor, the texture, also the mass density, whether it's a solid, liquid, or gas. Does it dissolve in water? Does it conduct electricity or heat? Is it magnetic? And so we'll talk a little bit about malleability. Does it bend out of shape or does it fracture apart? Can you pull it into wires or does it just break? And heat capacity is a measurement of how much energy it takes to raise the temperature. Some things change temperature very easily. Other things require a lot of heat before they change temperature. So that is a physical property. So as we do these classifications, we would want to ask, are the properties and composition constant? If yes, it might be a percent. Oh, honey. Annie, did you have a question?
Yes, I do. I was wondering if distillation is specifically referring to using boiling to separate substances, or yeah, or if it's any processes.
No, it's changes in boiling point.
Specifically boiling point. Okay,
Yeah.
thank you.
Yeah. To you again. So if you have one place to take notes, that's probably handy. All right. Okay, so just to summarize what we've been talking about, if it's a pure substance, we can break it down between, we can decide whether it's an element or a compound. And to take a compound and break it down into an element, into those elements that it's made out of, that is a chemical change. When we separate a mixture into its pure substances, that is a physical change. And then in a mixture, we tend to determine whether it's heterogeneous, has lumps, or homogeneous, it's very smooth. So sometimes it can be hard to tell the difference between homogeneous mixtures, like coffee with cream in it, or pure substances. I can't think of a pure substance that looks like coffee with milk in it. But sometimes those can be hard to tell. For example, if you have pure salt versus salt with sugar, you can't tell just by looking. Like we could tell by tasting it. Of course, we'll never taste anything in the lab. But that's an example where we can relate to that. Okay, some chemical properties. And again, many of these may be unfamiliar. We're going to study these, but we have an acid-base kind of reactivity, and that is just observed that like lemons are sour, and the skin of blueberries is a little bit bitter. So those are acid and base type compounds. Does it eat things up and destroy them? Is it corrosive or caustic? Is it reactive, like it changes right away in air or water? Or is it very stable, like salt? Table salt can sit on the table for years. It never changes. It's very stable. Does it explode? Does it burst into flames? Those are all chemical properties. And then we have oxidizing and reducing. That's another axis of reactivity that we will study. All right, we can also describe things as solid, liquid, or gas. And that's going to be a big focus for us. So I'll pick up with this